Hi there, welcome back to Classical Mechanics. Let's start Chapter 2. Imagine you are being chased by a monster and your only escape is to jump out the window to the sea. Using Newton's equations, you can calculate the equation of motion. Mass times acceleration on the x-axis is equals to your mass times g, the gravity of the planet where you are. I'm considering positive downwards in the direction of the acceleration. This you already know. But let's make it a bit more realistic. We know that there is drag due to air, likely there's air to breathe. So we need to account for this drag. A good quantitative description of drag is that each force is proportional to the velocity of the falling object. The more velocity, the more opposition, the less velocity, the less important drag will be. So the force of friction can be written as minus mkv, minus because it opposes the motion, and k is the proportionality constant. This constant will depend on the fluid, air, on the material of your clothes, and on your shape. The new differential equation to solve now is mg minus kmv equals to ma. So let's solve this differential equation. The mass cancels. We write acceleration as dv dt, separate variables and integrate. We get the time as a function of velocity. Let's assume that at time equals to 0 speed was 0. I solve for the velocity and get the velocity as a function of time. Now I can continue and write the velocity as dx dt. Separate variables again and integrate. So I get the position as a function of time, the equation of motion. The position depends on time linearly but also exponentially. Let's analyze this a bit more. The exponential term increases quickly at the beginning but then tends to a limit value. So it is for short times when the exponential term is relevant and comparable to t, both contribute in a similar way. But for large times, e to the minus kt tends to 0, so the position increases linearly, but with an offset. If we plot the velocity versus time, we see how this reaches a limit, terminal velocity. So after a while you'd be falling at constant velocity, you wouldn't be experiencing any acceleration. This differs considerably from the previous solution that didn't consider air friction, and it is more realistic. May the science be with you.